Hello, this is Dr. Zachary Roman, and I would like to thank you for joining me for another multi-level modeling lecture. So today we will be continuing with our second lecture on analysis of longitudinal data. So we'll start by reviewing polynomial effects and quadratic effects mainly in regression, and then we will take a look at the multi-level modeling options. This will be a relatively shorter lecture, but we'll focus a little bit more on a practical application in R today. So, very simply put, in regression, quadratic effects are included with a squared term. So here I'm using t as our predictor. This is simply a vector of time, just like from the last lecture. Okay, so this would be measurement occasions, time 1, 2, and 3, etc., predicting some outcome. This is a means of looking at a curvilinear growth trajectory. So let's take a look at what interpretations in quadratic effects look like in regression. So these are just typical growth trends, and what I have here is the quadratic slope on these panels at the top, B2. B1 here is the linear slope. So let's go back and look at that equation here. So we have B1 on the x-axis panel and B2 on the y-axis, on the top panel, okay? So this is the quadratic term. This is the linear term. Let's practice interpreting these. So let's start here at 0. And you know what, let's do 0, 0. So when the quadratic and linear term are both 0, we have no relationship between time and the outcome variable y. So we have a 0 slope. When the quadratic term is 0 here and the linear term is -6, we have a negative slope here. And again, it's linear because we have no quadratic effect. -3, it's a little less steep at +6, okay? So here's what our linear slopes look like in a quadratic model when this term is estimated to be 0. We have no curvilinearity. So let's move it up a little bit. So when the quadratic term is +3, we can see the trend is rising and it is accelerating. The -3 slope here for the linear term tells us the slope of the fitted line at 0. This is why I have the dotted lines here. So the linear term tells us the slope at 0. We don't talk about much calculus in this course, but if you're familiar with calculus, this is the slope of the tangent line at 0. So it's the idea that because this is curvilinear here, if there was a slope, what is the slope of this line at exactly 0? And see how at -3 for the linear term, this tilts our fitted line. So we have a negative association at 0, but we have a positive association for the curvilinearity. So this is accelerating. Notice the difference here. So staying with the -3 term, so still -3 is the slope of the tangent line. When the quadratic term is 6, we see more acceleration. We have a tighter parabola, okay? So let's take a look at the inverse here. When B1 is still +3, -3, so we still have this negative slope of the tangent line here. -6, the sign gives us an idea of the direction of the influence. So the linear line tells us nothing about the direction of the parabola, but the quadratic line tells us about the sign gives us the angle of the parabola, if it is accelerating or decelerating, going down or up. And the linear term simply tells us the slope of the tangent. So go ahead and take a look at these examples. Make sure you understand how they all fit. Now, I dropped the intercept here from this plots, but simply the intercept is still the predicted value of y when these terms are 0. And I dropped that from this by constraining it so that the expected y value at 0 is always 0, okay, just for simplicity. Now, we can include more polynomial trends. So I just showed you quadratic, and we'll probably just be working with quadratic for the most part, but we'll definitely take a look at some cubic terms. But in theory, we can include t minus 1 polynomial effects, where t is the number of time points. And so let's take a look at this. If I only have 2 time points, I can only estimate a linear effect. But if I have 3 time points, I can potentially estimate a quadratic effect, or of course this direction. With 4 time points, I can estimate a cubic effect. At 5 time points, I can estimate a quartic effect. So you can only estimate at most t minus 1 effect, quadratic or polynomial effects in a regression model. So let's review multi-level models for longitudinal data. Recall that now in longitudinal models, we treat level 1 as measurements. So these are the times. The measurements in time are level 1. In level 2 are people level. So this is the individual, or where we are pulling the measurements from. Variables at level 1 are time specific. So they vary with time. These are time varying covariates as well as the outcome. At level 2, we have variables that describe the individual subjects. So these are consistent over time. And sometimes these can be baseline measures such as depression, but also things that are truly stable like gender, etc. Okay. So the goal of longitudinal analysis is to find a model that best fits our average developmental trajectory. So this is the growth across time, and the individual slopes. Now, the individual slopes part is new in MLM compared to traditional ANOVA or MANOVA or any of the other contrast methods. And it is represented in the model implied covariance matrix. So in MANOVA, the modeling of means, you model the means using polynomial contrasts. However, in MLM, we can model the means and the covariances using polynomial fixed and random effects. What does this mean? Well, we can actually model the covariances or the relationships between parameters, and we can do this using polynomial fixed or random effects, and of course linear as well. So what is our goal? Our goal is to understand and explain the developmental trajectories. There is variability in developmental trajectories here across time, and we aim to explain that or reduce the unexplained variability. For example, using a fixed slope. This is a quadratic slope that I fitted to this data here, and this slope would be, this is the fixed effect or a fixed quadratic effect. This is akin to regression. The average, this is the average developmental trajectory of all of our cases. All right, so recall, as many polynomial mean trends can be tested as there are different time points minus 1. Okay, this is akin to ANOVA or MANOVA. But in addition, in MLM, we can test t minus 1 random effects, and this refers to the elements of the variance-covariance parameters. In this case, if we include all of them, no residual variance can be estimated. The model would be saturated for the covariance matrix. So we want to use less than t minus 1 random effects. Practical restrictions apply due to measurement error. What do I mean by saying this? Well, if we're fitting very high level trends, as in like to the 5th power, picture the curvilinearity of this. It is very important to consider the accuracy of the measurement in the instruments that you're using, because polynomial trends are relatively prone to overfitting. That means explaining variance by explaining error, typically just subsumed by measurement error. If we have relatively messy data, it's relatively easy to fit a curve through that, which will explain a minute amount of more variance. However, it's likely just with our own sample. And so it's important to use theory when estimating higher level polynomial effects, something suggesting that the mean will go up and then down and then up and then down again due to, some theoretical consideration. Because, in psychology, we typically will use measurements with relative error. Right, compared to more objective measurements like temperature or weight. By using survey instruments and things such as this, we end up with measurement error. And because our data is then considered a little messy, we are susceptible to overfit, where higher level polynomial trends might suggest more information or that they're explaining variance, when in the end, another sample likely wouldn't yield the same result. So my advice here is, we should consider theory first and foremost in curvilinearity effects before going for a purely data-driven approach. And I'll say this with all modeling in general. The decisions we make should have some grounding in the theory we have. If I think growth is exploding, like we're measuring weight during puberty and people are growing tall and getting heavier, a quadratic effect makes sense. And so theory should ground our decision-making in our data analysis as well. So just some things to consider when we're inserting a ton of potentially higher order polynomial effects. Another consideration to have in mind will be a callback from last week, which is centering. So time and centering is very important. Recall the example from last week here, where we see that depending on where the 0 point for our vector of time is, the estimate of the random intercept can vary drastically. Here we have the same data, but just by centering the time variable, depending on where we're centered, we would have a non-significant or very small random effect variance of the intercept here, or larger. Now, it's important to keep this in mind in curvilinear effects as well, because with curvilinear fixed effects, the linear term, or B1 from our earlier examples, will now reflect the slope at 0. And so we need to really keep in mind where our 0 points are with the time vectors, because it will now change the interpretation of the random intercept as well as the interpretation of the linear fixed slope, okay? Because it's the linear fixed slope tells us the slope of the tangent line at 0. And while we're at it, because it will impact the random intercept, it would also impact the parameter for the covariance between the random intercept and other random terms. So all things to keep in mind here. And we will play with this when we get to the R example. All right, so let's get to MLM. Let's include polynomial effects in our multi-level modeling equation. I say linear models are often oversimplified because frequently we will note linear trends, but this could only be in a restricted range of data. When we look at the relationship between IQ and how much money you make, for example, it might be linear within the range of average individuals and even very intelligent, maybe low intelligence individuals. But it might become nonlinear, as in a very high slope at the very, very high end, or the very, very low end, it might have a much lower slope. So people with very low intelligence might make very little money. And people with very high intelligence might make a lot of money. Very, very super genius people. And so linear trends might explain data within restricted ranges, but likely at extremes with some things, we may see, nonlinear relationships. So let's take a look at a quadratic model, or how we would model these non-linear relationships in a multi-level situation. So here I have two algebraic formulations here. So I have the multi-level model, and then here I simply re-term the model, or reformulate it. Okay, so this is the same model. So let's take a look. We have our average intercept, our average slope of the linear term for time, and then our slope of the quadratic term for time. Simple. This is the regression equation I presented earlier, but now with our multi-level subscripts. When I reformulate it, however, take a look at what we see here. So in this formulation, we see that the intercept is still isolated. However, the slope at 0 is dependent on time itself. So where the second line here indicates that the time trend depends on the time point. The time trend varies as a function of time. So with level 2, we now have a fixed intercept. So this is the average intercept, the variance of that intercept by individuals, the variance of the slope of the linear term here for time, the variance of individuals, the fixed slope of the quadratic effect, and then the variance of the individuals. And so quadratic trends can occur in the overall level at gamma 2, 0, so the fixed effect, and or at the random level. So let's tie this back to some data. If we have y and then time, our gamma 0, 0 here is the expected value of y when time is equal to 0. And I've done a poor job of centering time here. Notice we have time 1, 2, 3, 4, 5, and 6. So time 0 is over here. This is a conversation we'll have in the R example. So the expected value of y when time is 0. And then this is our U01 term here, our variance term, tells us what that variability is. On average, how much variation, or how much do individual cases differ from the fixed intercept value, okay? Now, we have the fixed slope. This is the slope of the tangent line at 0. So what is the average slope of cases at 0? Then we have the variance of that. How much does each case's slope at 0 vary? Right here, the variation of the linear term regarding time, right? And then we have the fixed quadratic effect, right? So this is telling us the curvilinearity, the direction, and the magnitude of the curvilinearity. This term is the variance of that. So how much, on average, is each individual varying from the term? If this is very high, we would see some trends accelerating, some accelerating less, some accelerating more, right? If this is very low, these trends, as it is here, will fit the fixed effect quite well. Let's talk about the intercept again. So if the variance here of the intercept, or if the random term of the intercept is high, cases will have very different values at 0. At baseline or at time 0, we'll see a large variability in the intercept. If we have a very different slope at 0 for the linear term, the variance, if it's very high, some cases will have negative slopes, some will have high, we'll have just a lot of variability in the slope at 0. And again, with the quadratic term, if it is very high, some slopes will see much larger developmental trajectories and other flatter developmental trajectories. Okay, now this left out the relationships between the random terms, or the covariances between the random terms. So let's visualize these as well. The covariance between the random intercept and the random slope at 0. So if this is a high value, it means the higher your intercept score, the higher your slope at 0 tended to be. So let's pretend time 2 is 0 now. This would suggest that the higher up your intercept value, then the higher your slope at 0 will be. If this is negative, the lower your intercept is, the higher your slope will be. Okay, let's look at the covariance between the random intercept and the quadratic term. This would mean the higher your intercept is, the stronger your developmental trajectory is, or the more curvature you're seeing. And the lower your intercept is, the less curvature you're seeing. Here with this term, the covariance of the slope at 0 and the quadratic term will tell us if this is positive, the higher your slope at 0 is, the higher your curvature is. And the lower it is, the flatter your line is. Inversely, if it's negative, the lower your slope is at 0, the higher the curvature you'll see. And the higher you are, the less curvature you'll see, or the flatter. Okay, so those are the covariance parameters between the random effects. Just a little more calculus for us. So these accelerating and decelerating trends will depend on our positive or negative effect of the fixed quadratic term, gamma 2, 0. And the trend flattens out at the partial derivatives here. Okay, so if you're familiar with calculus, at the partial derivatives here of this function, our trend flattens out. And so this is the average trend, gamma 1, 0. So the flat, the slope at 0, plus 2 times the slope, the quadratic term, to the tth power. And it flattens to 0 here. So just a few more things to keep in mind here. Terms in polynomial models are going to be highly correlated. Okay, so if I have a vector and I square it, there will likely be a high correlation between those two vectors. So for balanced designs, we can center by subtracting the mean at time. So if we have 6 time points, we can subtract 3 to mean time center. See, we always center before squaring. And this will result in less correlation between our quadratic term and our original term. However, this changes the interpretation for things now. The intercept represents, instead of a baseline score, it represents the subjects at the middle time point. And this can be more or less desirable, depending on the study. I've done multi-level work with a weight loss study, and time 0 is a very informative time because that represents the weight of people prior to engaging in the weight loss study. And so it was actually quite important for us to have information regarding the intercepts at time 0 and the slopes at time 0. And so this wasn't an option in that circumstance, and it may not always be for you. So we'll look at this again in the R session we do. But centering is an option. However, if it's not, because we really want that baseline information, we have another option, and this is called an orthogonal polynomial. This is more generally a procedure referring to orthogonal polynomials. And they have the advantage that coefficients for different time trends are on the same scale. This is like z-scoring or standardizing coefficients. And their contribution can be assessed more easily. We do this by doing a Cholesky decomposition. And this is used to transform a time trend matrix to an orthogonal contrast matrix. And so S will be the Cholesky factor of the matrix T, the time matrix. The new matrix, T times S prime inverse, will include our orthogonal contrasts. So this keeps the scale of time consistent. We can always get back to the original scale of time, but it results in an uncorrelated design matrix. Also, and when I say design matrix, I'm referring to the vector T and T squared, but it could also be T cubed and T quartic. And the more terms we have, the more reasonable Cholesky decomposition will be to produce an uncorrelated matrix of predictors. I present this to you because this is a really useful trick, method, and it's really your only solution for having a highly correlated polynomial set of predictors. That being said, it's a little complicated, and I think it's beyond the scope of our class, but feel free to contact me if you ever want to discuss it. There's also some great information in the Hawks textbook, our required textbook, on approaching this. So a little beyond what I think is typical for the course, but a really, really useful approach if you're doing high-level polynomials. All right, that's all I have for the polynomial lecture for today. Let's now move over to the R session where we'll take a look at some of this in action. Thank you very much.